Hey everyone, Amin here with AI Plays. Today we're covering the Edge Enhancement filter. Let's get started. To recap, so far we've covered how a camera converts light into a bare domain image, how to correct dead pixels, how to compensate for black levels, how to adjust for lens shading, what an anti-aliasing filter is and how to apply one, how to apply auto-white balance gain control, how to convert the bare domain image into a full RGB image, how to adjust the lightness scale to make a more visible image, how to convert color spaces from RGB to YCBCR, how to apply a noise filter to the chroma channels, how to adjust the hue and saturation of an image, and finally, how to apply a noise filter to the luma channel. The Edge Enhancement filter we'll be discussing today is easily the most innovative and amazing module covered in the entire ISP pipeline so far, and the techniques we'll cover are actually used in edge detection algorithms well beyond the ISP, even in some advanced applications like medical imaging to read MRI and X-ray scans. The purpose of the Edge Enhancement filter is to make the edges of an image pop out and appear more visible, and we do that by increasing the luminance level of all of the edges while keeping the chrominance values the same. This way, although edges will reflect the same color in the finalized image, the edges themselves will appear more crisp and clear-cut. The method we'll use to increase the luminance level of all of the edges is to generate an edge map. The easiest way to understand what an edge map is by seeing it yourself. This is the edge map of the color checker image that we'll generate in this video. It's a completely black and white image, where if there is no edge at a specific point, that point is black. And if there is an edge, depending on the strength of the edge, the point becomes white. This edge map can then be scaled and added on to the original luminance channel. Since the spots without edges are black, it means their pixel value is 0, so adding a 0 to the original image will have no effect. On the other hand, the spots with edges are white, meaning their pixel values are non-zero, so adding them to the original image will strengthen the edges. The challenge in the Edge Enhancement filter is generating an edge map programmatically, since it wouldn't be much of an ISP pipeline if some dude had to draw edge maps with a white color pencil for your camera to work. So how do we detect edges and how do we convert them into a full edge map? As you may have guessed from the name of the video, we'll be using filters. Let's again turn to this 5x5 snippet of the luminance channel of our image. Just like in the noise filter for Luma, pretend that there is an edge here on the pixel column P4, such that everything to the left of the P4 column is white and everything to the right of the P4 column is black. Finally, the filter for today will be this linear 3x3 filter, with positive ones all across the right, zeros down the center, and negative ones across the left. What is very important to notice is that the sum of all of the values in this specific filter add up to 0. Also to review, since this is a linear filter, it will be applied using the usual convolutional with kernel tactics, where we multiply each value in the extracted area with its corresponding value in the filter, take the sum of all 9 values, and then map that value onto the center pixel in a copy of the image. When a filter is applied on pixel P7, the final resulting value is 0. Why? Well, the middle column can be ignored since it gets multiplied by 0, and since all of the values in the 3x3 area are the same or very similar, the 3 pixels in the right column minus the 3 pixels in the left column is roughly 0. This would show up as black on our edge map, which is exactly what we want since there is no edge here. Having the sum of a no edge area add up to 0 is exactly why it is so important that all of the values inside the filter add up to 0. Now watch what happens when we bring the filter to pixel P8. Now again, the center row is ignored, but the right and left columns are very different. And when you calculate the difference, the result is close to negative 750. Very much not 0. Using this filter, depending on whether you are entering into a brighter or darker area, you will get a negative or positive value for your edge. To make it appear properly on your edge map, we generally take the absolute value of the resulting value from the edge filter. Besides the need for the absolute value though, this filter does have one actual major issue. It only works for side-to-side edges. Imagine the first 2 rows were an edge instead, and you were dealing with pixel P7. Despite the fact that you are on an edge, the filter will return a value close to 0. One option is to also run a similar filter flipped 90 degrees. The original horizontal filter will now be responsible for generating a left and right edge map, while this new filter will be responsible for an up and down edge map. You could then add the 2 edge maps into one finalized edge map and move on from there. And while this would sort of work, you run into errors with diagonal edges or curved edges, and it becomes very computationally heavy. A better solution is to instead improve the filter. Take this 3x3 filter with an 8 in the center and negative 1s all around it. Again, all of the values in the filter add up to 0, so using the same demonstration with vertical edges as before, when the filter is applied to pixel P7 where there is no edge, the resulting value is 0. However, when we move to pixel P8, we get a positive edge, and then at P9, you also get a negative edge. In fact, this is true whether we are entering a lighter or darker area. You will always get a positive and a negative edge back to back. This is because unlike before, where you were comparing values from outside and inside the edge, now you are comparing differences in all surrounding values relative to a single center pixel. This gives you a certain freedom as well. If you want thicker or more pronounced edges, you can apply an absolute value to your filter. If you would like light enhancement to your edges, leave out the absolute value. Just remember, if your edges are too thick, the image will start to look blocky. The most important point about this filter, though, is that it works in all directions. If we place the filter on pixel P7 with the horizontal edge from before, this filter still picks up the edge. In fact, even if we have a diagonal edge or a curved one, this filter can still get the job done. Now once you have your edge map, you can't just simply add the edge map onto your existing image. After all, values of edges in your edge map are likely well over your maximum allowed value in your base data type, since you multiplied your center pixel by 8. Instead, you multiply your edge map by a scaling factor k, then add the scaled edge map to the image to produce a finalized result. Now let's have a look at the code. The EEF function takes as input the luminance channel after the noise filter for Luma that we generated in the previous video and the correction factor k. It outputs the EEFY, which is the luminance channel after applying the edge enhancement filter. We start as usual by changing the data type of the image to accommodate large values, extracting the rows and columns to iterate over, adding the image to give corner pixels neighbors, and copying the image. Additionally, we also create an empty array for the edge map, and we initialize the filter. In case I didn't mention it previously, this type of filter is called a Laplacian filter. Next, we start on the main loop. At each pixel, we extract a 3x3 section of the image, multiply it with the filter, and store that value into the edges array. Then, as an extra step to avoid noise pollution, we scale the edge map to get rid of any weak edges and multiply by k. Finally, we add the edge map to the original image and reset the data type to uint8. This is the resulting image after the edge enhancement filter with a k value of 0.75, and the edges around the color boxes do look a bit clearer and crisper. For a stronger effect, as we mentioned before, you could use absolute values when applying your Laplacian filters. And that's it for today, everyone. Next time we'll cover contrast brightness control for the final video in this series. Have a good day.